Okay, so yeah, so my talk is about the second incompleteness theorem in rather general circumstances, and the question how much we still retain of Lbs logic in these more general circumstances. So yeah, the talk touches a lot of subjects. So one thing that always fascinated me is the role of the third Loeb condition. Provable implies provable, provable. So we are not going to look at circumstances where we do not have this third Loeb condition. Also, so one thing that fascinated me always was the question of the relationship between the two great modal logics for fixed points, namely modal logic for guarded fixed points, to wit Loeb's logic, and modal logic for fixed points with where the fixed point variable occurs positively, to wit the mu calculus. So somehow all these threads come together, I think, in what I'm going to talk about. So, but let's first, to set the stage, look at a classical version of Gödel's second theorem. So, so this is the modulo a little bit of added by me. This is Fairfield's formulation of the second theorem in his 1960 arithmetization paper. So his main idea is we fix a proof predicate. So let's call it proof of big X of little x of y. So big X is a second order variable, or a unary predicate symbol that is a free parameter in the arithmetical definition of proof. And then we plug in specific definitions for the axiom set to get provability for alpha. And so then Fairfield's version says, well, consider any consistent RE theory T, and consider any interpretation of a sufficiently strong weak arithmetic. And in this case, for Fairfield's theorem, we need elementary arithmetic, so I delta 0 plus exponentiation plus sigma 1 collection. And suppose that you have a sigma 1 definition of the axiom sets. And so semienumeration simply means that if something is an axiom, then the theory proves that it is an axiom, right? It's just that. And then if under those circumstances that we have that the theory doesn't prove its own consistency. So it turns out, so it's a little bit annoying that you need sigma 1 collection, but it turns out that you can omit it, but then you have to change, then you need a different proof. And that's one thing that I'm talking about now. So if you look at the Fairfield style formulation, you see that it has some restrictions, right? So we know that we have the second theorem for oracle provability, the provability notion associated with omega consistency, cut-free provability, and elementary arithmetic over elementary arithmetic, etc. So we have, of course, that EA elementary arithmetic plus sigma 1 collection is a rather strong base. So we would like to have something weak like S12. And certainly, of course, we have the role of this specific formula class sigma 1. So we are going. So what I'm going to show you is a somewhat more general result, but it's still Fairfield style. So it works for predicates of the form prof alpha, that where the alpha will satisfy some further condition. But for example, we do not need that provability here will satisfy the Loeb conditions. Okay, so maybe one brief word about general versions of the second incompleteness theorem. So I think no mathematical theorem has a most general version. So there's always just a kind of big cloud. There's always a kind of big cloud of versions. And in the case of the second incompleteness theorem, I think you can I think we can go in we can go in extremely different directions in generalizing it. So I'm not claiming that I'm doing the best thing possible here. Okay, so okay, so okay, so yeah, still a little bit about Fairfield proof. So so it does employ the Loeb conditions for provability, and so I have a counterexample that this fails in elementary arithmetic. So we have a sigma 1 axiomatization of elementary arithmetic, such that elementary arithmetic proves that the set of axioms is finite. And it does prove that the provability of consistency is equivalent to the inconsistency. And it also proves that, oh, sorry, it does not prove that provability of inconsistency is equivalent to inconsistency. So this means that the Loeb conditions fail, right? Because we did, this is a theorem, it is a theorem of Loeb's logic. And certainly we can prove that the Gödel sentence is the consistency of inconsistency. And more generally, we can prove that Gödel sentences are unique. So that's one example. So you see that for Fairfield's result, we really need the collection axiom. So there's also this example due to Fairfield, and that's the warming up for my general version. So Fairfield gave an example of a pi01 axiomatization of piano arithmetic that for which we do not have the second incompleteness theorem, right? So the idea is very roughly, so let pi be the standard predicate representing the axioms of PA. Then we take pi of x of y, that y is an axiom and it is smaller than x, smaller or equal than x. And then we define the new definition, the new, so pi star. So Fairfield being a Fairfield axiom is simply to be an axiom, but also you demand that the finite theory axiomatized by that axiom is consistent. And so, so note, since this pi is of course very simple, it's in fact, well, it's delta 01, it's elementary, it's as simple as you may wish. So that's so the whole thing, pi star is pi01. It enumerates the axioms of PA and PA, but we do not have the consistency. So why? Yeah, so it's mysterious. So how did the Fairfield axiomatization escape the second theorem? Well, if you look at what's going on, then you see that if you want to verify that the first k axioms are indeed axioms, you need more axioms. So the axioms needed to verify that certain axioms are more than the axioms of which you verify that they're axioms. But since we have infinitely many axioms, so we can always add axioms to verify that something else is an axiom. So so it shows that this restriction to sigma 1 is needed in Fairfield theorem, but it also gives us a hint of how to for this more general formulation.
Okay.
So
I interrupt you for a second with a question. Could you go back to your formulation of your theorem?
Fairfield theorem. This one?
Okay, your version of Fairfield theorem. So what do you mean by semi-enumeration?
I tried to say that. So it just means that if A is an axiom, then the theory proves sigma k of A, right? Mm-hmm. That's all you need.
One way.
Yeah.
From left to right. Okay, and then if you go back to.
Well, because the point is, the point is, of course, if it's more, then it gets more difficult to be consistent, right? So you don't need to have the if and only if.
Yeah, okay. So it actually enumerates some extension of T, so you can say that.
Yes.
Okay. But if you go now to your counter example, so
that
did I get
numerator,
it right that it's about B sigma 1 there? So the failure of B sigma 1 allows for such a counter example. So the Craig's trick does not work for.
So in this, and so in this case, in the counter example that I, for time's sake, cannot show you because it's it uses Solovay's theorem, or the construction of Solovay's theorem. It's a subtle example, but so there you do have simply numeration, right? The sigma numerates. It's not semi-numerates. It's an exact numeration. In the standard model, it gives you precisely the axiom of EA, but still you get this thing. And of course, you cannot. The important
but once you have EA plus B sigma 1, that will be not a counter.
Precisely. It's the sigma collection that does the trick.
Okay, good.
Yeah?
Yeah.
Okay, so now escaping this, now the important insight. So if you look at Fairfield's example, so that the axioms escape, the axioms proved to be axioms need more axioms to prove that they are axioms. So this kind of thing is all that goes wrong. So if we define what I call uniform semi-numeration, we are fine. And so what is semi-numeration? So let's go to the consider our consistent theory U, right? And let X be the set of Gödel numbers of axioms of U. So, and there's no constraint on the complexity of X at all, right? So X could be sigma 1, 2, X could be pi 10,500, X could be even outside any classification that we have. So the X could be as complicated as you want. And so let UK the theory axiomatized by the elements of X that are smaller or equal than K. And suppose we have an interpretation of a suitable weak arithmetic. And I always take buses S1, 2, but take your own favorite in U, right? So we have to speak about numbers somehow. Now we say that formula Xi uniformly semi-numerates X with respect to N if for every N we can find a bigger M such that UM proves Xi I for every I in XM, right? So the whole point is, so for any finite subseries, we can find a slightly bigger finite subseries such that finite subseries, the bigger one, proves that all its axioms are actually axioms, right? So that's as soon as you take some finite subseries, there is always a larger one that escapes the mechanics of the Fairfield counterexample, right? So that's precisely what we demand. So, and if we have this, then we get my general version. So suppose U is consistent, and suppose Xi uniformly semi-numerates the axioms X of U with respect to N, of course, then U does not prove the consistency of Xi. So I put Xi between square brackets to remind us, simply as a reminder, that we do not, so the relativization to N is for the proof, etc., right? So the formalization of provability, but it's not for Xi, right? Xi is not a formula that lives inside N, but it could be a completely general for any U formula that satisfies the properties. And so, let's B be the single sentence that axiomatizes N. And now we get the proof of the general version. And it's, if you see how frighteningly simple this proof is, it's a little bit surprising that it was not found by Fairfield when he wrote his arithmetization paper. But I think the main thing is that he simply didn't ask the question that leads to this version, and well, one reason he didn't ask this question that he didn't know all these examples of oracle provability, etc. That was still in the future, I guess. So, so suppose that U proves its own consistency, then for some K0, of course, K0 proves the interpretation of the axioms of sigma 1 plus the consistency, so for some finite thing. But then we can go one up to K, right? So for K0 to K, to find a theory that proves the consistency statement and the interpretation of S12, and such that also Xi semi-enumerates Xk in Uk. Now then we simply take beta as the trivial axiom that says that something is in Xk, right? It's simply a finite disjunction. And then it's very easy to see that the theory UK proves that if something is beta provable, then it's also Xi provable, right? Because it's only a finite verification. So it's a standardly finite thing, right? That the axioms, the beta axioms. And so it follows that UK proves B and con beta N, where and now con beta is really the consistency of UK. And so, but now we are home, because this is the second incompleteness theorem for finitely axiomatized series. And of course, so take any of your favorite proofs. So this contradicts the standard version of G2, and we are done, right? So you get so the main thing here is simply, I think, this formulation of this notion of uniform semi-enumeration that does the trick, because as soon as you have it, the proof is that's completely simple. So the example that I showed you shows that the provability, the Xi proof need not satisfy the loop conditions. Still, the loop conditions are used in the proof, right? So so we do not have the loop conditions for the provability predicate, but of course, in using the standard version, we use the loop conditions or any other proof of the second incompleteness theorem that uses something like the loop conditions or something that is equivalent to it. Okay, so now, so this was the point where I was, and so I think as more or less an afterthought, I noted that, of course, uniform semi-enumeration is in a trivial way extendable to finite extensions. And so we have a little bit more, right? We also have Lbs Rule, right? So if U proves that A is Xi provable, then that if U proves that if A is Xi provable, then U proves A, right? So so we have Lbs Rule also in this kind of very general context. So now something happened. So I read a paper by Salehi and Layevardi, and so this paper was about the uniqueness of the Gödel sentence, the well-known uniqueness proof, and so I thought, well, of course, that also goes overboard in my more general context, and so I tried to use this example here to find the counterexample, but it turned out that that the uniqueness theorem still holds here, and so and so that automatically leads to the question: so what is the so yeah, why is that so, and can we understand that modally? And so that leads then to the formulation of the Hankin calculus. So what is the Hankin calculus? Well, it's really simply it's the weakened version of Lbs logic, right? So we have axioms and rules, the axioms and rules of K. We have Lbs rule. We have the equivalence of formulas that result from each other by renaming bound variables. And we have the fixed point axiom. So we have we add a fixed point operator to the language, and we add the fixed point axiom that tells us that the fixed point of box phi is equivalent to the result of substituting the fixed point of box phi in box phi, right? So that's the fixed point axiom. Okay, maybe something, yeah, I'm going to say more about this in a moment. So if you look at the third axiom that really is about renaming bound variables, it turns out that if you do this, these fixed point logics, the whole thing with the binding, etc., is more or less hopeless, because if you leave that axiom out, you get nowhere, right? Because you cannot easily prove that renaming bound variables gives you equivalent formulas, and so it's a headache to the bound to have the bound variables here, and I really wonder whether all these versions of the mu calculus, for example, have it right, and whether they didn't forget to add some action about renaming variables. Okay, so yeah, so the Hankin calculus, as I formulate it here, has the kind of standard syntax, but after I submitted my abstract, I discovered that you can that you can also do it differently, and so it seems to me that the Hankin calculus is not at all about binding, but it's about circularity. And so what you also could do is change the syntax and work with cyclic graphs, and it seems to me that they do represent what's going on much better, and so that treatment would be co-inductive in spirit, but I think the disadvantage is, of course, discontinuity with the more conventional treatments that do not have the cyclic graphs. But yeah, I'm hopeful, because I'm now working on how to translate back and forth between non-cyclic graph versions and standard syntax versions, and I think that should be very well possible. Okay, so yeah, so I'm not going to talk about the circular Hankin calculus, but let's just a brief look at what the axioms look like, right, of the circular calculus. So you simply have the axioms and rules of K, you have Lbs rule, and you simply have that if two formulas are bisimilar, then they're equivalent. And so the bisimilarity axiom is really not an axiom, because it simply expresses our idea, of course, that the true formulas are simply the object's modulo bisimilarity. But I'm not going to really talk about it, but at least.
What is bisimilarity here?
Well, very simple. A formula is in this setup is a graph, a directed graph with ordered successors. And then the notion of bisimilarity is simply that a rooted one, of course, a rooted directed graph, rooted connected directed graph with ordered successors and labels. And bisimilarity is simply bisimilarity in the usual thing, right? It simply have the back and the force condition in the usual way. It's precisely what you would think it is, right? So if you have two nodes, if two nodes are bisimilar, and if you have the ordered successors of both nodes, well, if they are bisimilar, they have to preserve the labels. If you take the successors of both nodes, then the corresponding components also should be bisimilar, right? That's the Zig and the Zag condition. Yeah.
Okay. Okay.
Yeah. So
negation is allowed in the language here, right?
Yes. No problem. It's negation. Yeah. It's completely the standard language. The only thing is that we have the circularity, and so we do not have, of course. So we do not have the fixed point operator, right? That's now handled by the circularity of the syntax. So there's no headaches with bound variables anymore. So and also I think a lot of things like unravel, a lot of constructions that we know from about bisimilarity, etc., like unraveling, etc. A lot of pleasant things suddenly become available, and yeah, many things get easier. Okay.
It's not even obvious that the last principle is consistent, but okay.
It is consistent. Yeah, sorry. Okay, yeah, you're completely right. Of course, I'm not telling you everything, right? So what we demand of the graphs, of course, is that every cycle contains a node labeled with a box, right? We need the guardedness condition, of course. Is that what you were missing, right? The formula should be guarded. That means that a cycle in a formula needs to have a box somewhere.
Yes. Okay, that makes it more plausible. But okay, you simply omitted quite a lot of explanations here.
Oh yeah, well, I just wanted to hand wave at this because
I don't want to stop your talking.
The talk is not about the circular syntax, but I simply already wanted to advertise it.
Let me just mention that in the paper with Dania Shamkhanov, that was about abstract versions of G2 in the context of weak logics. We did have a version of this fixed point, as you call it, Hankin Calculus, and exactly the same two problems appeared with substitution, with renaming and substitution, and without. And there it was handled by kind of circular proofs.
Right. Yeah. So that's one thing I didn't do yet. So of course the circular formulas are begging for circular proofs, right? But I didn't. Yes. I didn't add these yet. Okay, but so now back to the ordinary language, and so so what we can do then is add what I call the Grullet modality. So I call it Grullet because in my macros, the gray circle is called Grullet for gray bullet. So so the Grullet modality is really the fixed point of box phi and p, where p is not free in phi. And so that the nice thing is, of course, that for the Grullet modality we have Lbs logic, and we can prove in the Hankin calculus the de Jong-Sambin-Bernardnik theorem, right? So that tells us that if P is equivalent to phi, and if Q is equivalent to phi, sorry, the dot here is the usual thing for, so box dot means, box dot phi means box phi and box phi, right? So the box is the strong version, the conjunctive version of the necessity operator. So if you have P if and only if phi, and provable P if and only if phi, Grullet provable P and only if phi, and similarly for when this the case for Q, then you have these things are equivalent, right? So we can in the Hankin calculus verify the de Jong-Sambin-Bernardnik theorem. And that already tells us that the Gödel and Hankin sentences are unique, right? So so that's the uniqueness theorem. And so what you can also do is solve equations. So suppose that we have a number of equations, P0 if and only if phi 0, Pn minus 1 if and only if Pn minus 1. So we can solve these equations. So what you do is you form a graph for the system of equations, namely if pi is a fixed point variable, you make an arrow to pj if there is an unguarded free occurrence of pj and phi I, if and only if. And so then we say that the system of equations is guarded if the graph is acyclic, and then you can prove, in fact, by quite conventional methods, that if E is guarded, it has a unique solution. So, of course, the fixed point variables disappear in this solution. So that's the solving systems of equations. So here you have such an example, right? So P if and only if not Q and R, Q if and only if box P and box R if and only if Q and S. And then you see the graph. So from P, we have an arrow to Q and an arrow to R because they occur unguarded. But then in Q, all the variables are guarded. And in R, we see Q. And S doesn't appear because it's not a fixed point variable. And you see that there's no cycles in this graph, so we will have a unique solution in the logic. And so using this, we can do the following. It's a bit of work, so I'm also hiding. I'm hiding some details here again. So given that you have phi, you can produce an equivalent phi such that you can provide a phi tilde such that phi is equivalent to the substitution of boxed formulas for certain fresh variables, where then in phi tilde the fixed point variable doesn't occur, right? So there is a small, the detail I'm hiding is so what about the boxed formulas that occur inside the scope of a fixed point variable? Of course, you have to move them. You have to move the boxes out first before you can do this. And so if you then look at the equations that P if and only if phi tilde and Q0 if and only if box psi 0, etc. So if you solve that system, then you find that it has a fixed point, and so and that fixed point gives us immediately a fixed point for phi. And so you see that in the Hankin calculus, where we only have officially fixed points for boxed formulas, we also get fixed points for modalized formulas, right? So the existence of boxed formulas implies the existence of modalized formulas. And so we could form the extended Hankin calculus where we add not only fixed point for boxed formulas, but also for modalized formulas. And then you can show that these two calculi are synonymous, right? So the simple version and the richer version are the same. And so the nice thing again of the circular syntax is that the whole business of solving equations disappears. Those versions are simply the same, right? So the difference between them disappears. Okay. Now, yeah, so we can give arithmetical interpretations in the usual way, but well, yeah, no, maybe that is too strong. It's not really the usual way. So we can give arithmetical interpretations, but it needs a bit of work. So you need the something like the multiple fixed point theorem in arithmetic. And so and handling free variables, etc. It's a little bit more complicated to do the arithmetical interpretations than in the ordinary Lbs logic case, but you can do it. And so we simply have that the Hankin calculus is for every whenever we have a uniform semi-numeration of the axioms, then the Hankin calculus is arithmetically valid. And so in all these cases, we have, for example, the de Jong-Sambin-Bernardin theorem of the uniqueness of the fixed points. So the Hankin calculus and the extended Hankin calculus both have a simple Kripke model completeness theorem in the finite directed acyclic graphs and in the finite trees. We will see in a moment an extremely quick proof of this. So the Hankin calculus also has uniform interpolation, etc., etc. So that seems to be quite an achievement, but as you will see in a moment, it's completely trivial. But so what is of course open is the thing about the provability logic. So I only really have a few examples in which the full power of the Hankin calculus, the full richness of the Hankin calculus is needed. But so I think thinking about the arithmetical completeness is a win-win situation, because either it's arithmetically complete and that would be a beautiful result, or it's not, and it would be extremely cool to see an example of a principle that we have over and above the Hankin calculus in all uniformly axiomatized series. Okay, so now, I see that I'm doing good in time. So this is already the last stretch. So now, one thing that completely independently of this whole work on the Hankin calculus. So one thing that I really always found fascinating is so we have modal logic, right? Start with K, and now we add fixed points with using D gamma, but we don't add Lbs rule because that gives you the Hankin calculus. So what constraints on fixed points will give you a consistent theory? Now the best thing I know is that the constraint should be the most liberal constraint I know is that the things outside the scope of a box should occur in positive places. The fixed point variable outside of the scope of the box should be positive, right? So I think that's the richest constraint, but I have no idea of, and I don't know whether anybody has some theory about the space of possible conditions on your fixed points formulas that do the job. But there are two big ones, right? So the one of them is guarded. So the fixed point variable only occurs in the scope of a box. That's a guard. And the other one is that the fixed point variable only occurs positively. So and so if you have guarded, then you get the Lbs logic. But as we have seen, if you have guarded more generally, we have the Hankin calculus. But so you could also say we look at positive places, and then we have, as a famous system, the mu calculus, and so that has the fixed point axioms that I showed, but not Lbs rule, but it has the minimality rule, which is in some sense very much analogous to Lbs rule. So the thing says that so if P occurs positively in phi, and if phi alpha implies alpha, then the fixed point of phi, the minimal fixed point of phi implies alpha, right? So think of Tarski-Knaster right? So that it really tells you that the minimal fixed point is the intersection of all prefixed points. Okay, and now the nice thing is, so now here is where Hankin certainly turns up. So take the mu calculus Hankin sentence. So the smallest p such that p is provable. And that's, if you look at mu plus h semantically, that's precisely the well-founded part of the mu calculus. So the Hankin sentence means foundation. And now the surprising thing is that the mu calculus plus the Hankin sentence, so the well-founded part of the mu calculus, so to speak, is simply the same thing as the Hankin calculus. So these two calculi coincides. And so they're synonymous in a strong sense. You can translate them back and forth. And so, and it also means that many famous theorems can be simply transferred from the mu calculus to the Hankin calculus. For example, we can use the completeness theorem that we have for the mu calculus to give a completeness theorem for the Hankin calculus, since the mu calculus satisfies uniform interpolation, and that's preserved when we add h as an axiom. Then we have also uniform interpolation in the Hankin calculus, etc. Yeah, I'm again a bit sloppy here, so I'm not. I mean, of course, h is added as an axiom, right? Not as an assumption. That's important. Okay, so of course I cannot sketch you this, but as a last thing, so I think so how do we, why does, so how, so the mysterious thing is, so how can this be, right? So we have the modalized fixed points and we have the positive fixed points. Now, so what is well known in the mu calculus is that we can restrict the mu calculus to modalized fixed points, but then still positive for positive variables, right? It's a well-known theorem there. So it's so that's not, well, that's, I thought that was surprising too, but it was not. It was already in the tradition. So the mysterious thing is, so how can we get fixed points also for negative places in the mu calculus? And so we can see this as follows. So for the mu calculus, you can formulate a solution lemma just as the one I showed you for the Hankin calculus. And so you again make a graph in the same way, but only now the demand is that if you have a cycle that the let's see. So if we have a fixed point variable, and in the fixed point formula, a fixed point variable p, and if a fixed point in the fixed point formula q occurs positively, we add an arrow labeled with plus, and when the q occurs negatively, we add an arrow labeled with minus, and then the solution condition is simply that that if you have a cycle, then the number of minuses should be even, right? So that's it. And you can then prove the solution condition. So the interesting thing is that the fixed points this construction delivers are not necessarily minimal fixed points. You can give easy counterexamples for that. So the construction does it shows that the mu calculus has many more fixed points. So I think in the context of the mu calculus, so this is a version of Bakich lemma, but I think it's slightly stronger formulation than the usual one. So now suppose that phi is modalized in P, so P is only in the context of a box. So what you do is on the one hand, you replace the negative occurrences of P by a fresh Q, and on the other hand, you replace the positive occurrences in phi by a fresh Q, right? So you separate the positive and negative occurrences by renaming the one class of occurrences with Q, but you can do it in two ways. And so this gives us phi 0 and phi 1. Now look at the equations P if and only if phi 0 and Q if and only if phi 1. So this can be solved in the mu calculus because you can see that the graph that I show you is the graph of the pair of equations, and you see that it satisfies the cycle condition, right? So we every cycle has just an even number of minuses, so we can solve this. Now let the solutions be alpha 1 and alpha 0 and alpha 1, but in mu plus h we have we can verify, because we can verify in fact Lbs rule, that we have Lbs rule. And so from that we have the uniqueness of the modalized fixed points. So in mu plus h, the two fixed points are the same. So this means by substitution of equivalence, which we do have in the mu of provable equivalence, which we do have in the mu calculus, that oh sorry, I forgot. There should be an h here, of course, right? So we have that that mu plus h proves alpha 0 if and only if phi 0, and then substitute alpha 0 for P and alpha 1 for Q, but since alpha 0 and alpha 1 are equivalent, this could also be alpha 0. And then if you meditate on the definition, you see that this is phi of alpha 0, and so alpha 0 is a fixed point of phi. So there you see in action how well-foundedness is stronger than negativity, right? So as soon as you have well-foundedness, then you can ditch, you can throw away the negative fixed points. And so the Hankin calculus turns out to be the mu calculus plus the Hankin sentence. And that's also one reason that I call it the Hankin calculus. Okay, so yeah. So summarizing, so first I proved the stronger version of the second incompleteness theorem. Then the series turned out to be satisfy Lbs rule. So and then the question emerged. So what is the logic of this? And at least the obvious logic that is sound for that is the Hankin calculus, and the Hankin calculus turns out to be quite an interesting calculus. So yeah, I'm reasonably sure this all works. So I'm nearly done working out also the version with the circular graphs, and so the fact that both versions work, I think, is strong evidence that there are no big mistakes left in the whole work. But so of course there's still a lot to do, and especially a lot of examples. So for example, Kurahashi has a lot of examples with sigma 2 axiomatizations of PA and PA, but he didn't add the fixed point operator. But there's a rich store of examples where you can wonder what happens with these examples when we add the fixed point operator to them. So there's still a lot to do. Well, that's what I wanted to say.